The ultimate fate of the universe has long been a subject of wonder and inquiry, one that challenges our understanding of space, time, and matter. In this section, we embark on an exploration of black holes and their profound, sometimes perplexing, role in cosmic evolution. We begin by delving into the mysterious nature of black holes, the cosmic titans that warp space-time, and then pose the provocative question: could these gravitational monsters, which so effectively swallow stars and planets, eventually grow large enough to engulf the entire universe? By establishing the foundational concepts behind black hole physics and outlining the central questions of our discussion, this section sets the stage for a deep dive into one of the most fascinating puzzles in modern astrophysics. Gravity, mass, and density. What is a black hole? A black hole is essentially defined by the extraordinary interaction of three concepts: density, mass, and gravity, that go against our common sense. According to Einstein's theory of general relativity, mass and energy cause space-time to be bent, which is why we feel gravity as a force that pulls objects together. Once a large star runs out of nuclear fuel, it can't withstand the force of gravity anymore. With a tremendous collapse, the star's core shrinks to a very tiny volume, and space-time curves so steeply that a zone arises from which not even light can escape. The event horizon defines the boundary of this area. The magnitude of a black hole's gravitational attraction is directly proportional to its mass. The tremendous density of matter due to extreme compression produces a gravitational pull so strong that evasion is impossible after the event horizon is crossed. One strange thing about black hole physics is that the event horizon of a black hole enlarges as its mass increases, whether by absorbing matter or merging with other black holes. The average black hole density drops as a result of the event horizon expanding. An extraordinarily high average density would be the consequence, for instance, of a black hole with the mass of our Sun having an event horizon of just a few kilometers. Supermassive black holes located in the galactic core can be as massive as millions or even billions of suns, but have incredibly low average densities, sometimes even on par with air. This seemingly irrational behavior exemplifies the peculiarities of black hole physics, where the density-mass connection deviates from the norm. Within the framework of black holes, the notion of density is inextricably bound up with the concept of a singularity, that is, the exact location in the middle where, according to classical physics, density becomes infinite. This infinite density is not a real condition, but rather a signpost showing the collapse of our physics theories, according to what we know now. In actuality, the event horizon is the point at which our standard conceptions of space and time break down. Formation of black holes, stellar collapse, and beyond. Most black holes are made when huge stars fall apart under their own weight. The heart of a star closes in on itself when the nuclear fuel inside it runs out and the star can't fight gravity any longer. This fall is so terrible for stars with masses more than about 20 times those of the Sun that it causes a supernova explosion. The star's outer layers are blasted into space, and the core gets much smaller until it turns into a black hole. During this process, the core changes into a very small object where gravity is very strong. An event horizon forms around it, which is a line beyond which no matter or information can escape. Besides the breakup of massive stars, other ways of creation have been suggested. One of these channels is the straight fall of very large gas clouds in the early universe. If the conditions are right, these clouds can skip all the steps needed to turn into stars and go straight into a black hole. This process is seen as one of the most likely ways that supermassive black holes, which are found at the cores of galaxies and have masses of millions to billions of solar masses, came to be. Since they were formed so early in the past of the universe, it seems likely that these kinds of direct collapse processes must have happened very soon after the Big Bang to build up mass on these huge scales. The creation of primordial black holes is another interesting option. These made-up things might have come about from changes in the universe's density long before the first stars and galaxies formed. Primordial black holes would have a wide range of masses, unlike black holes that form when stars fall apart. They could be the start of later structure formation, or even add to dark matter. It's still not certain if they exist, but they offer an interesting way to connect astronomy and high-energy physics. Black holes can also grow and change by merging with other black holes. When two black holes hit each other, they join together to make one bigger black hole. This process not only helps supermassive black holes get bigger over cosmic time, but it also makes strong gravitational waves that ripple through spacetime. Observatories like LIGO and Virgo have directly picked up on these signals. These mergers tell us a lot about the population numbers and natural past of black holes in the universe. These four ways that black holes form: stellar collapse, direct gas cloud collapse, primordial beginnings, and mergers, show that the process is complex and can happen on a huge range of sizes and times. They show how the extremes of gravity can show up in different places, from the quiet beginnings of the universe to the violent deaths of stars. To fully understand not only the life cycle of black holes, but also how they affect the structure and growth of the universe as a whole, you need to understand these processes. Event horizons and the Schwarzschild Radius. The event horizon is the most important idea in black hole physics. It is a line in space-time beyond which nothing can escape the black hole's gravity. The event horizon is not a real surface. Instead, it is a mathematical line set by the Schwarzschild Radius, which is the critical distance from the center of a black hole that is not moving. What this radius is based on is the black hole's mass, and anything matter or radiation that gets too close can't go back. The Schwarzschild solution to Einstein's field equations provides a simple yet profound expression for this radius. Specifically, the Schwarzschild radius RSR SRS is given by RS equals 2gmc squared, S equals C22gm, I d sub S equals 2gm, divided by c squared, where g is the gravitational constant, m is the mass of the black hole, and c is the speed of light. This formula illustrates that the size of the event horizon increases linearly with mass. However, as a black hole grows, its average density decreases, leading to the curious result that supermassive black holes, despite having enormous mass, can exhibit relatively low average densities. The curve of spacetime becomes so extreme once an object crosses the event horizon that all future paths must lead to the singularity. This is where traditional physics breaks down. These models say that the rules of physics as we know them stop working in normal ways past the event horizon, even though we can't see what happens there. Light, which usually shows us what's going on in the universe, can't get out of this area, so black holes are basically invisible. This is the reason why scientists use secondary proof, like gravitational lensing and X-ray emissions from matter falling into black holes, to figure out if black holes exist. Hawking radiation and black hole evaporation. In the 1970s, Stephen Hawking introduced a groundbreaking idea that forever altered our understanding of black holes. They are not entirely black. Instead, quantum effects at the event horizon lead to the emission of what is now known as Hawking radiation. This concept arose from combining principles of quantum mechanics with Einstein's theory of general relativity, revealing that even seemingly inescapable black holes can slowly lose mass over time. Hawking radiation originates from the turbulent quantum vacuum that pervades all of space. According to quantum theory, the vacuum is never completely empty, but is instead a seething froth of virtual particle-antiparticle pairs that constantly pop in and out of existence. Near the event horizon of a black hole, the intense gravitational field can separate these pairs before they have the chance to annihilate one another. In some instances, one of the particles is drawn into the black hole, while its partner escapes into space as real radiation. From an external observer's perspective, it appears as if the black hole is emitting particles. This process has very important effects. Black holes slowly lose mass because each particle that escapes takes energy away from them. This process is called black hole evaporation. The rate of evaporation is strongly related to the mass of the black hole. Smaller black holes give off radiation more quickly than bigger ones. The evaporation time for stellar mass black holes is very long, much longer than the age of the universe itself. On the other hand, if tiny black holes exist, they could evaporate much more quickly. Hawking radiation's mathematical foundation is both beautiful and somewhat startling. Hawking developed an inversely proportional black hole temperature using quantum field theory in curved spacetime, using which as opposed to its mass. This implies that the temperature of a black hole rises as it shrinks and loses mass, therefore accelerating the rate of radiation emission. This feedback loop implies that black hole evaporation can turn into a runaway process if it reaches a critical mass, producing a last blast of energy. The implications of black hole evaporation extend far beyond the fate of individual black holes. Over extremely long timescales, as black holes slowly radiate away their mass, they contribute to the overall thermodynamic evolution of the universe. In scenarios such as the heat death, where the cosmos approaches a state of maximum entropy and uniform temperature, Hawking radiation is a key mechanism by which the energy locked in black holes is gradually returned to the universe. This process ensures that even the most extreme gravitational objects cannot remain permanent fixtures, but will eventually fade away, adding to the inexorable march toward a cold, dark, and static cosmos. But the idea of Hawking radiation also begs fascinating questions. One of the most well-known is the black hole information conundrum, which queries whether, during evaporation, the knowledge about the matter falling into a black hole is lost permanently or somehow maintained. With hypotheses ranging from holographic principles to modifications of quantum theory, this conundrum has stimulated a great lot of theoretical study aimed at reconciling the seeming loss of information with the fundamental laws of physics. The paradox of density. Large black holes are surprisingly thin. Black hole physics has among its most baffling features the link between mass and density. When we typically think of objects growing larger, we expect their density to remain constant or even increase. However, black holes defy this intuition. Whether by merging with other black holes or by accretion of nearby matter, a black hole's event horizon grows as it gains mass. The average density of the black hole actually falls as the volume contained by the event horizon rises more quickly than the new mass. Consider a stellar mass black hole, which might have a radius of only a few kilometers. The matter compressed into this tiny space yields an extremely high density. In stark contrast, supermassive black holes, such as the one residing at the center of our Milky Way, span millions of kilometers across. Despite having millions or even billions of times the mass of our Sun, their average density can be surprisingly low, sometimes comparable to the density of water or even air. This phenomenon arises because the Schwarzschild Radius, which defines the size of a non-rotating black hole, scales linearly with mass. As a result, when the mass increases significantly, the corresponding increase in volume, which scales as the cube of the radius, outpaces the mass accumulation. This strange behavior has huge effects on how we think about gravity physics and the organization of the universe. It shows that black holes are not the solid, very dense things we might think they are when they get really big. Instead, they turn into very large, fluffy areas of space-time, where the pull of gravity is spread out over a very large area. The fact that giant black holes are very thin goes against what we normally think and helps us understand how mass, space, and gravity work together in general relativity. This strange increase in density with mass is also a key part of many theoretical talks about black holes and their place in the universe. It supports the idea that, on big enough scales, even the average density of the universe we can see might be low enough to keep areas far from huge clusters from collapsing due to gravity. Accretion and mergers. Growth mechanisms. Black holes don't stay the same after they form, they're always changing. There are two main ways they gain mass and size: accretion and mergers. When a black hole sucks gas, dust, and other types of matter into itself, this is called accretion. As this stuff swirls inward, it makes an accretion disk, which is a whirling, flattened shape that is heated to very high temperatures by gravity and friction. The disk's extreme heat makes it give off high-energy radiation, mostly in the X-ray range. This is one of the most important ways to tell that a black hole is active. As time goes on, matter from the disk falls into the black hole, making it heavier. This causes the event horizon to get bigger. This slow process is one of the main ways that black holes get bigger, especially in places with a lot of gas, like the centers of galaxies. Accretion is not merely a quiet, steady inflow of matter. It can also trigger dramatic, high-energy phenomena. In many cases, the inflow of material is not uniform, leading to instabilities in the accretion disk. These instabilities can result in episodic bursts of radiation or the launching of powerful relativistic jets that extend far beyond the black hole itself. Such jets, which are observed in active galactic nuclei, provide compelling evidence of the dynamic processes at work near black holes. They transport energy and matter away from the central regions of galaxies, influencing the interstellar medium and potentially regulating star formation on larger scales. Another important way that black holes grow is through mergers. When two black holes get close to each other, their gravitational pull pulls them together in a dance through space that ends with a crash. When galaxies crash into each other, bringing their center black holes with them, these mergers can happen. As galaxies join, black holes spin inward, losing energy by sending out gravitational waves, which are ripples in spacetime that have been directly found in the past few years. When two black holes finally merge, they make a single, bigger black hole whose mass is about the same as the sum of its predecessors' masses, minus any energy that was sent out as gravity waves. This process not only makes the black hole heavier, but it also changes the way gravity works in the host galaxy. The merging process is inherently violent and can have significant implications for the dynamics of the surrounding environment. During a merger, the tremendous gravitational forces at work can disturb nearby stars, gas clouds, and even entire stellar systems. These disturbances may trigger new episodes of star formation, or conversely, eject stars into intergalactic space. Moreover, the energy released in gravitational waves provides a unique window into the physics of black holes. Observatories such as LIGO and Virgo have captured these fleeting signals, confirming that black hole mergers occur and offering insights into the masses and spins of the colliding objects. Even though they are two different processes, accretion and mergers are very linked in the life cycle of black holes. It takes billions of years for black holes to gain mass because they slowly take in matter from their surroundings. This happens in many galaxies. In some systems, especially those with a lot of galaxies, mergers are more important. This is because black holes collide and join together as galaxies evolve. The bigger picture of how the universe works affects both processes. For example, mergers happen more often in the early universe, when matter was more densely packed together. This helped supermassive black holes grow very quickly. In older galaxies with less gas, on the other hand, accretion may be the main way they grow. All of these growth processes show how black holes can grow from small pieces of stars into some of the biggest things in the universe. the slow build-up of mass through accretion, and the sudden, powerful events of mergers not only shape the growth of black holes, but they also have big effects on how galaxies form and change over time. As we keep improving our observations and computer simulations, these processes will stay central to our understanding of what black holes do in the universe. Supermassive versus ultramassive black holes, scale and characteristics. Large black holes are very different from very small ones. This difference is especially noticeable when you look at supermassive black holes next to ultramassive ones. Supermassive black holes are usually found in the middle of galaxies. They have masses that are millions to billions of times heavier than the Sun. They play a big role in how their host galaxies change over time. They affect how stars and gas move around, and sometimes power the powerful events seen in active galactic centers. But even within this group, there is an interesting range. Ultramassive black holes are the heaviest and most mysterious black holes. They can have masses that are hard to imagine, sometimes exceeding tens of billions of solar masses. How the physical properties of these giants scale with bulk is one of the most fascinating things about them. An event horizon's limit, the Schwarzschild Radius, grows in proportion to the mass of a black hole. An event horizon will grow in size in direct proportion to the mass of a black hole. The average density of a black hole decreases with mass increasing because volume rises with the cube of the radius. Consequently, stellar mass black holes are extremely dense, but supermassive and ultramassive black holes can have shockingly low average densities, which are even lower than Waters or extremely low-mass black holes. Since more mass usually indicates more density, this seemingly contradictory connection shows that black holes' bulk characteristics function differently. Observations of the centers of galaxies provide compelling evidence for these phenomena. For example, Sagittarius A star, the supermassive black hole at the heart of the Milky Way, has a mass of roughly 4 million suns and an event horizon spanning only about 17 million kilometers. Yet, when we look at galaxies in more active or massive environments, we encounter black holes that dwarf Sagittarius A star in both mass and size. In some cases, ultramassive black holes, those at the extreme end of the mass spectrum, are estimated to have masses exceeding 40 billion solar masses. Their vast event horizons extend over distances comparable to the size of entire solar systems. Despite their enormous mass, the average density of these ultramassive black holes is astonishingly low. The matter is spread so thinly across the expansive event horizon that the gravitational pull is more distributed than concentrated. What this event means for our understanding of gravitational physics is very important. The fact that black holes' densities drop as their masses rise goes against what we normally think about matter and compression. This shows that black holes are not normal things. They are instead very skewed versions of spacetime, where the rules of classical physics give way to the strange rules of general relativity. Their features not only help us understand how galaxies form and die, but they also bring up important questions about what matter and gravity are like in very harsh conditions. The places where these black holes reside also have an effect on their development and growth. Interactions and mergers happen a lot in the dense cores of galaxies, which can cause mass to build up quickly and sometimes create ultramassive black holes. The interaction between accretion and galactic dynamics, which includes the impact of dark matter, shapes not only black holes, but also the development of the galaxies that house them. Feedback from black holes' activities, like the release of high-energy jets, can sometimes control how stars form, and even change how matter is distributed on a large scale. Observational techniques detecting the invisible. It's not easy to see dark holes because they don't give off any light. Instead, scientists use a group of indirect methods to find and study these mysterious objects. Gravitational lensing is one of the best ways to do it. This is when the light from background objects is bent and warped by a black hole's strong gravity. A black hole's gravitational field works like a cosmic lens when it passes in front of a faraway star or galaxy, briefly making the light bigger and warping it. Researchers can figure out the existence and mass of black holes even when they can't be seen directly by looking at these lensing effects very carefully. Another important observational instrument is the investigation of nearby black hole high-energy emissions. Matter from an accretion disk flows inward, heating to millions of degrees and radiating copious quantities of X-rays and gamma-ray. By capturing these emissions, spaceborne observatories such as the Fermi Gamma-Ray Space Telescope and the Chandra X-ray Observatory enable scientists to locate black holes and investigate their feeding behaviour. Apart from verifying the existence of black holes, the radiation from accumulating matter offers understanding of the dynamics of the inflowing matter and the very severe physical conditions close to the event horizon. Radio observations play a critical role in detecting the activity of supermassive black holes. Instruments like the Event Horizon Telescope, EHT, have imaged the shadow of a black hole by capturing the radio waves emitted from hot plasma around its event horizon. These observations offer a direct glimpse of the warped spacetime near a black hole and help constrain theoretical models by comparing the observed shadow size and shape with predictions from general relativity. Numerical simulations and modelling black hole dynamics. Direct observations of black holes are very helpful, but most of what we know about how they move and change is based on complicated numerical models. Scientists can use these computer models to simulate and study black holes in a controlled setting. This gives them information that they can't always get from just looking at them. Scientists can study how accretion flows form, mergers happen, and gravitational waves are made during these exciting events by modelling the development of black holes over very long periods of time. Numerical simulations incorporate the equations of general relativity to model the curvature of spacetime around black holes. These simulations can capture the intricate details of how matter spirals into a black hole's accretion disk, how turbulence within the disk influences radiation, and how the dynamics change as black holes merge. Advanced algorithms and powerful supercomputers enable these simulations to resolve fine-scale structures and track the evolution of black holes from their formation to their eventual growth through mergers. In doing so, they reveal the non-linear interplay between gravity and fluid dynamics and help predict observational signatures such as the emission of high-energy radiation and gravitational waves. Interpreting data from gravitational waves is one area where numerical modelling shines. Collisions between black holes cause ripples in spacetime known as gravitational waves, which observatories like LIGO and Virgo are able to detect. The waveform of these signals may be inferred from simulations of these mergers, which in turn allow researchers to estimate the masses and spins of the merging black holes. We learn more about the physics behind these cosmic occurrences when scientists compare their models with real detections and compare the resulting waveforms. Simulations provide a testing ground for alternative theories of gravity and modifications to classical models. As new physics is incorporated into these computational frameworks, researchers can explore how changes in the laws of nature might affect black hole behaviour. This iterative process of simulation and observation forms a feedback loop that continually advances our knowledge of these mysterious objects. The role of black holes in galactic evolution. Black holes are not separate events. They are closely connected to the development of galaxies. There is a giant black hole in the middle of most, if not all, big galaxies. Its mass is millions to billions of times that of the Sun. The huge objects have a big effect on the space around them and control how the stars, gas and dust in the home galaxy move and interact with each other. Their pull on the stars helps shape their paths and can even start or stop bursts of star formation. Black holes are very important to the life cycle of galaxies because they do these things. In galactic nuclei, the gravitational force of the central black hole governs the motions of nearby stars and gas clouds. When gas is funneled toward the galactic center, often due to interactions or mergers with other galaxies, it forms an accretion disk around the black hole. The energy released from the infalling material heats the disk to millions of degrees, emitting copious amounts of radiation that can be observed across the electromagnetic spectrum. This high-energy output can influence the surrounding interstellar medium by heating the gas, driving powerful outflows, or even generating relativistic jets. These jets, which extend far beyond the galaxy's core, can impact star formation on a much larger scale by compressing gas in some regions while dispersing it in others. Feedback from the central black hole appears to be a key ingredient in regulating the growth of the host galaxy. In many galaxies, the energy released during active phases, when the black hole is accreting large amounts of matter, can prevent runaway star formation. This process, known as AGN feedback, active galactic nucleus feedback, is believed to heat and expel gas from the central regions, limiting the raw material available for new stars. The balance between gas cooling and heating is delicate. Too much cooling can lead to rapid star formation, while excessive heating can suppress it, leading to a quiescent galaxy. Observations of galaxy clusters and simulations suggest that AGN feedback plays a critical role in maintaining this balance, thereby influencing the overall evolution of galaxies. Correlations in the real world, like the M-sigma connection, show how black holes are connected to the galaxies that house them. There is a link between the center black hole's mass and the spread of star speeds in the bulge of the galaxy. This suggests that the two are evolving at the same time. This strong link between the two events suggests that the birth of galaxies and the growth of black holes are closely linked, most likely through complicated feedback mechanisms. Basically, you can't fully understand how a galaxy changes over time without looking at how its center black hole affects it. Mergers and interactions between galaxies also serve as catalysts for both black hole growth and galactic transformation. When galaxies collide, their central black holes may eventually coalesce, releasing enormous amounts of energy in the form of gravitational waves. These dramatic mergers can rearrange the structure of galaxies, drive shocks through the interstellar medium, and trigger starbursts. The newly merged black hole, often more massive and energetic than its predecessors, then continues to influence the evolution of the resultant galaxy. In some cases, the disturbance from a merger may even eject the central black hole from its host galaxy, creating a rogue black hole that wanders through intergalactic space. Such events underscore the dynamic interplay between black holes and the large-scale structure of the cosmos. The evolution of galactic structure over cosmic time reveals that black holes are not merely passive sinks of matter. Instead, they are active agents shaping the distribution and evolution of stars and gas within galaxies. Their influence extends to the chemical evolution of galaxies as well. The feedback processes driven by black holes can redistribute metals produced in stellar interiors, enriching the interstellar medium and affecting subsequent generations of stars and planetary systems. This ongoing cycle of enrichment and feedback plays a fundamental role in the evolution of galaxies and the eventual emergence of complex structures, including those that might harbour life. The black hole at the centre of the Milky Way. A cosmic engine that has a significant impact on the dynamics and development of our galactic neighbourhood is Sagittarius A star, SGR A star, a supermassive black hole located in the centre of our Milky Way galaxy. Sagittarius A star controls the orbits of neighbouring gas clouds and stars with its strong gravitational attraction, which is unseen to the naked eye. in the dense galactic core, where stars orbit at incredible speeds, a sign of a vast, undiscovered mass. Its existence is deduced by careful measurements of stellar movements. Sagittarius A star is estimated to have a mass of about 4 million times that of our Sun, yet its event horizon spans only a modest distance in astronomical terms. Despite its relatively compact size compared to the entire galaxy, the influence of SGR A star extends far beyond its immediate vicinity. The intense gravitational field near the black hole not only shapes the orbits of stars, but also plays a crucial role in the dynamics of gas and dust in the central regions. This material often forms a swirling accretion disk around the black hole, heating up to extreme temperatures and emitting high-energy radiation in the process. These emissions, observed primarily in radio and infrared wavelengths, provide valuable clues about the physical conditions and processes occurring near the event horizon. Over the years, advancements in observational techniques have allowed astronomers to capture increasingly detailed images of the galactic center. Instruments such as the Very Large Telescope, VLT, and the Keck Observatory have tracked individual stars as they orbit Sagittarius A star, revealing not only the immense gravitational influence of the black hole, but also the intricate dance of matter in this crowded region. These observations have been critical in testing predictions made by general relativity, particularly concerning how gravity behaves under extreme conditions. The study of Sagittarius A star gives us clues about how giant black holes interact with the galaxies that house them. There are real-world connections between SGR A star and the Milky Way that show they have changed together over billions of years. One example is the M-sigma relation, which connects the center black hole's mass to the way stars move in the galactic bulge. This co-evolution seems to be controlled by feedback mechanisms, where the black hole's energy output controls the birth of stars and the movement of gas around the galaxy. In addition to its dynamic role, Sagittarius A star also provides a natural laboratory for exploring the mysteries of extreme physics. The environment near the black hole is a testing ground for theories that merge quantum mechanics and general relativity, as the conditions at the event horizon push the limits of our understanding. Ongoing and future observations, including efforts by the Event Horizon Telescope, EHT, aim to image the immediate surroundings of SGR A star with unprecedented resolution. Such studies are expected to refine our models of black hole accretion, jet formation, and spacetime curvature. Cosmic expansion versus black hole gravity. Black holes have a strong gravitational pull on a small area. The universe, on the other hand, is affected by a different force, cosmic expansion. Dark energy is what makes this growth happen on the biggest levels, pulling galaxies apart over time. The strong, limited gravity of black holes and the constant speeding up expansion of space create an interesting dynamic that changes the structure and history of the universe. On one hand, black holes represent regions where gravity is so strong that it overcomes all other forces, trapping matter and light within their event horizons. Their gravitational influence is concentrated in relatively small areas, and while they can capture nearby objects, they do not affect the overall structure of space on large scales. In contrast, cosmic expansion operates uniformly across the entire universe, stretching space itself and increasing the distance between galaxies. This expansion is observed through the redshift of light from distant galaxies, indicating that the universe is not static, but is continuously growing. The critical point of comparison lies in the scale and influence of these forces. While a black hole's gravity dominates in its immediate vicinity, its effect diminishes with distance. In the vast expanses between galaxies, the repulsive influence of dark energy takes precedence, driving galaxies apart at an accelerating rate. This means that even though black holes can grow large by accreting matter and merging with one another, they remain localized phenomena, unable to overcome the expansive forces at cosmic scales. The overall density of mass in the universe as a whole is very low, and this includes all black holes. Because the universe is so light, its general gravitational pull is weak compared to the force of its growth. Basically, black holes can greatly change the space-time around them, but the huge, mostly empty areas of space can grow without any problems. Black holes, no matter how big they are, can't swallow the universe because of this balance. The universe as a black hole, a theoretical exploration. When we look at the universe's mass and density, it raises an interesting question. Could the whole thing be seen as a big black hole? Even though this is just a guess, it's an interesting theoretical framework that makes us think about the limits between black holes and the rest of the world. The basic properties of black holes are compared to those of the universe in this study. The goal is to find out if the mass of all cosmic structures could, in theory, create an event horizon on a global scale. Consider the concept of the Schwarzschild Radius, a measure of the size of a non-rotating black hole's event horizon. For any given mass, the Schwarzschild radius is defined by the relation r sub s equals 2gm divided by c squared. When we apply this formula to the total mass contained within the observable universe, the calculation yields a surprisingly large radius. In fact, estimates suggest that if all the matter and energy in the observable universe were concentrated uniformly, it would be more than enough to create an event horizon that encompasses, or even exceeds, the volume we can observe. This observation is counterintuitive because the average density of the universe is extremely low, often described as merely a few hydrogen atoms per cubic meter, which is far less than the density of typical stellar black holes. Still, these contradictory circumstances reveal more important realities. Since a lot of mass is crammed into a tiny area, black holes typically conjure images of high densities. Black holes' event horizons expand linearly with their mass as their size increases. Their volume increases by the cube of their radius. Stated differently, large black holes such as those seen in galaxy cores could not have very high average densities. Applying this tendency to the extent of the universe, should the visible universe decrease, its low average density would still be sufficient to produce an event horizon, a restriction in the cosmos beyond which there is no escape. In this way, there is the fascinating possibility, at least theoretically, that our universe may include black hole characteristics. The dynamic character of the universe adds even more complexity to this concept. Driven by dark energy, the cosmos is growing unlike a stationary black hole. This expansion suggests that the constant stretching of space-time prohibits a simple collapse into a single, stationary event horizon, even if the total mass of the cosmos is sufficient to generate a black hole. Stated differently, although the mass of the universe points to a black hole in principle, the observed acceleration in cosmic expansion shows that our universe is not acting as a typical black hole would. Rather, it may exist in a condition when the characteristics of black holes and expanding space interact in hitherto unforeseen ways. The theoretical exploration of a universe-sized black hole also opens up broader questions regarding the nature of singularities and the limits of our physical theories. If our universe were to be viewed as a black hole, then the familiar notions of a central singularity might be reinterpreted, raising questions about the origin of cosmic structure and the ultimate fate of space-time itself. Such discussions push the boundaries of classical general relativity and invite speculation about quantum gravitational effects that might resolve these apparent contradictions. Critical density and the mass of the observable universe. Our knowledge of the behavior of the cosmos on the biggest dimensions depends mostly on the concept of critical density. Theoretically, critical density is the level at which the gravitational attraction, of all the stuff in the universe precisely balances the pace of cosmic expansion. Practically speaking, it is the average density the cosmos needs to be flat, neither expanding indefinitely nor finally collapsing back on itself. Calculating the average density of the visible cosmos reveals shockingly low values, that of few hydrogen atoms per cubic meter. Still, the mass contained inside the great extent of the visible cosmos is astonishing given such a low density. To appreciate this, consider that the observable universe is a sphere with a radius of roughly 45 billion light-years, containing hundreds of billions of galaxies, each with billions of stars. When the mass of every star, planet, gas cloud, and even the dark matter that permeates these galaxies is combined, the total mass reaches numbers that seem almost inconceivable. Despite this immense total, the mass is spread out over an extraordinarily large volume, resulting in the low average density observed. This paradox, of an enormous total mass but a very low average density, has profound implications. For one, it implies that while the universe might seem too diffuse on average to trigger gravitational collapse locally, the total mass is still high enough that if it were somehow concentrated into a smaller volume, it could form a black hole. In fact, theoretical calculations show that the combined mass of the observable universe is more than sufficient to create an event horizon that would encompass the entire universe or even exceed it. This approach opens an interesting prospect: black holes stacked, or Russian doll. The Schwarzschild solution, a formula derived from Einstein's general relativity, suggests that an event horizon might develop if the complete mass of the cosmos condensed inside a critical radius. The mass of the whole visible universe might in principle fit a black hole. Although this is a highly idealized situation, it challenges our common wisdom on density and gravitational collapse. The mass in the cosmos is gathered into galaxies and clusters instead of being evenly distributed. The enormous stretches of apparently empty space dilute the total average. Calculations based on the Schwarzschild radius reveal that the total mass is enormously huge, even if the density is rather low, as simply volume of space determines this. This difference between local density and global mass distribution tests our intuition. It also begs interesting issues regarding the organization of the universe. Could it be that, on a large scale, our planet has traits of a black hole? If true, what does that suggest about the character of spacetime itself? Considering that the cosmos is not stationary makes the interaction of cosmic expansion and gravitational collapse much more fascinating. Dark energy's ongoing expansion balances the gravitational forces that may otherwise draw stuff together to create a black hole. The long-term destiny of cosmic formations depends critically on this harmony between expansion and gravity. Although the mass of the visible universe is theoretically sufficient to produce a black hole, the rapid expansion guarantees that the matter stays too scattered for such a collapse to develop spontaneously. Could the observable universe form a black hole? A fascinating and surprising theory challenging our knowledge of cosmic structure is the possibility that the observable universe may contain enough mass to create a black hole. The average density of the universe is shockingly low, only a few hydrogen atoms per cubic meter, which first makes us think the universe is far too dispersed to collapse under its own gravity. But given the great extent of the observable cosmos, the whole mass contained there becomes shockingly enormous. Theoretically, a black hole would arise from the concentration of all this material into a sufficiently compact area, generating an event horizon, a barrier beyond which nothing could escape. But this idea brings up an interesting paradox. It looks like the universe is expanding as we see it. This fast growth is caused by dark energy, which keeps matter spread out over huge distances. The total mass is very large, but because it is spread out over such a large area, the average density is too low for gravity collapse to happen normally. Basically, the universe's mass could make a black hole if it were squished together very tightly. But this isn't going to happen because the universe is still expanding. The concept of the observable universe itself plays a crucial role here. Our observations are limited to a sphere centered on our location in the universe, defined by the distance light has traveled since the Big Bang. Beyond this boundary, the universe may continue indefinitely, and the overall mass distribution might differ from what we infer locally. Yet even within our observable limits, calculations suggest that the total mass is so immense that if it were somehow confined, it could easily generate an event horizon larger than the sphere we observe. This theoretical exercise forces us to reframe our understanding of density and gravitational collapse. It emphasizes that the key factor is not the local density, how tightly matter is packed in a given region, but rather the total mass relative to the volume over which it is spread. In our universe, while local concentrations of matter, such as galaxies and clusters, can collapse into black holes, the average density remains insufficient for a universal scale collapse due to the vast distances between these regions. Dark energy also affects the mechanics of the growth of the universe, which adds another level of complexity. Over time, as space expands, even areas that might have been able to collapse become less concentrated. This makes it less likely that a big area will fall due to gravity. The speeding up expansion works as a balance, making sure that the universe doesn't just fall into a single, all-encompassing black hole, even though it has a very large overall mass. Nested black holes. Are we inside a black hole? The idea of nested black holes goes against what we normally think about the universe, because it suggests that what we see as the universe might actually be formed like a big black hole, or even that we might live inside one. This idea comes from putting together two facts that seem to be at odds with each other. On the one hand, the visible universe has an incredibly big mass that in theory would be enough to make a black hole if it were all gathered in a certain area. On the other hand, dark energy is seen to be growing the universe, which keeps matter from falling apart completely. Despite these two facts, an interesting idea has been raised. While small areas can collapse into black holes, the universe may actually be made up of black holes nested within a bigger, changing spacetime that itself has black hole-like traits. Before we can talk about this idea, we need to talk about the event horizon, which is the line beyond which no information can get away. The Schwarzschild Radius tells us how big an event horizon is for any mass that is on its own. After adding up the universe's mass and finding its Schwarzschild Radius, we find that the answer is surprisingly close to the size of the universe itself. Because of this, some scientists think that our world might be like the inside of a black hole, where the normal rules of space and time are very different. In this case, what we think of as the universe expanding might be like how space behaves inside the event horizon of a black hole, a place where time and space can behave in strange ways. The idea of nested black holes suggests a cosmic Russian doll structure. In this picture, smaller black holes reside within galaxies, and these galaxies themselves, along with the matter between them, could be part of a much larger gravitational system that mirrors the properties of a black hole. This hierarchical structure raises fascinating questions about the nature of boundaries in the cosmos. Could the event horizon of a supermassive black hole at the center of our galaxy be just one layer in a multi-tiered structure, ultimately culminating in an all-encompassing cosmic event horizon? While this hypothesis remains highly speculative, it forces us to confront the limitations of our current models. The conventional view of black holes as isolated objects may be an oversimplification when considering the universe as a whole. Instead, the interplay between gravity, cosmic expansion, and mass distribution may create a scenario in which the universe exhibits properties similar to those of a black hole, yet without a singular, static event horizon that traps everything indefinitely. Thermodynamics and entropy in black holes. The connection between thermodynamics and black hole physics has changed how we think about both of them. In the field of classical thermodynamics, entropy is a way to measure how chaotic something is, or how many tiny configurations it can have. The second rule of thermodynamics says that over time, the entropy of a closed system begins to rise, which moves things toward equilibrium. Black holes, on the other hand, add an interesting spin to this well-known rule. Black holes are thought to absorb everything that crosses their event horizons, but they can have a temperature and an entropy. This idea was groundbreaking when it was first put forward by scientists working at the interface of quantum physics and general relativity. In the early 1970s, theoretical work revealed that black holes are not entirely black. Instead, quantum fluctuations near the event horizon allow for the spontaneous generation of particle-antiparticle pairs. Normally, these pairs would annihilate each other almost instantaneously. But near the event horizon, the intense gravitational field can separate them. One particle may fall into the black hole while its partner escapes as radiation. This process, now known as Hawking radiation, implies that black holes emit energy like a black body and therefore have a finite temperature. The surprising consequence of this radiation is that, over astronomical timescales, black holes gradually lose mass and eventually evaporate, contradicting the once-held belief that nothing could escape them. Assigning entropy to a black hole was a bold step, and it led to the formulation of the famous Bekenstein-Hawking entropy formula. According to this relation, the entropy of a black hole is proportional to the area of its event horizon rather than its volume. This was a profound departure from the standard thermodynamic behavior observed in conventional systems, where entropy typically scales with volume. The formula is given by S equals K times C cubed times A, divided by 4gh bar, where SSS is the entropy, AAA is the area of the event horizon, KKK is Boltzmann's constant, CCC is the speed of light, GGG is the gravitational constant, and HH bar is the reduced Planck constant. This equation not only provides a way to calculate the entropy of a black hole, but also hints at a deep connection between gravity, quantum mechanics, and thermodynamics. The fact that entropy changes with area suggests that black holes are holographic by nature. This means that the data about everything that falls into a black hole may be stored on its flat surface instead of its three-dimensional volume. The holographic principle says that the physics of an area of space can be described by the degrees of freedom that live on its edge. This idea has led to a lot of study into that principle. These kinds of discoveries are changing the way we think about how the world stores and processes information. The implications of black hole thermodynamics extend further when we consider the eventual fate of the matter that falls into them. If a black hole evaporates completely via Hawking radiation, a puzzling question arises. What happens to the information about the matter that was swallowed? This is the essence of the black hole information paradox. According to quantum mechanics, information must be conserved. However, the apparent loss of information in black hole evaporation seems to contradict this fundamental principle. Resolving this paradox remains one of the foremost challenges in theoretical physics, and has led to the development of concepts such as black hole complementarity and the idea that information may be preserved in subtle correlations within the emitted radiation. The study of entropy in black holes also gives us important information about what will happen to the world in the end. Black holes add to the general rise in entropy on a galactic scale by giving off radiation that has mass. As the universe moves toward a state of maximum entropy, which is sometimes called heat death, black holes slowly disappear. This is one of the last parts of the story of how the universe has changed over time. All the energy in the universe would be spread out evenly in this end state. The moving parts that used to power galaxies, stars, and other structures would stop working, leaving behind a cold, dark, and still universe. The information paradox. What happens to ingested data? The black hole information paradox is one of the most famous problems in modern physics. It's caused by the apparent contradiction between what quantum mechanics says about black holes and how general relativity describes them. The idea of quantum mechanics says that information can be changed or jumbled, but it can never be lost. But black holes seem to erase the features of anything that falls into them just by being there. It is thought that once matter or energy crosses the event horizon, it can never be found again in the outside world. The information conundrum is this clash between the idea that information stays the same and what happens to matter in black holes. The paradox first emerged from the theoretical work on black hole thermodynamics and Hawking radiation. As we discussed earlier, Hawking's groundbreaking prediction showed that black holes emit radiation due to quantum effects near the event horizon. This radiation is thermal in nature, meaning it appears to carry no information about the particles that originally fell into the black hole. If a black hole were to evaporate completely over time through this process, the initial information about the ingested matter would seemingly vanish, leaving behind only a featureless thermal spectrum. This outcome directly contradicts the principle of unitarity in quantum mechanics, which asserts that the evolution of a closed quantum system is reversible and information preserving. Several theoretical methods have been put forward to solve the dilemma. At first, it was thought that the data might be lost forever, which would mean that quantum physics would not work properly. Physicists are very worried about this possibility though, because it would mean completely changing one of the most important ideas in modern physics. Instead, a lot of experts think that data must be kept somewhere, even if it's in a very jumbled state, and that what we know about black holes right now isn't full. Using the holographic concept is a hopeful way to solve the dilemma. This idea comes from string theory and black hole thermodynamics. It says that degrees of freedom on the edges of a volume of space can reflect all the information that is stored within that volume. This means that the information about matter that falls into a black hole might not be lost inside the black hole at all, but might be stored on the event horizon. Hawking radiation gives off the black hole's mass, which could cause the information stored on the horizon to slowly be sent back out into the universe, though it might be in a very jumbled and random way. According to the idea of black hole compatibility, there is no one objective way to explain what happens to information in a black hole. To someone outside the black hole, the Hawking radiation seems to be sending information away, but to someone falling into the black hole, they would experience a different, complementary world where the information stays inside. From this point of view, what seems like a loss of information is actually the result of trying to combine two different points of view into a single, logical story. Even though this method isn't perfect, it does offer a way to explain why different viewers have different experiences without breaking the basic rules of quantum physics. Recent developments in quantum gravity and string theory have further enriched the debate. The ADS-CFT correspondence, a conjectured duality between a gravitational theory in anti-de Sitter (ADS) space and a conformal field theory (CFT) on its boundary, has provided a powerful theoretical framework in which the information paradox can be addressed. In this dual description, a black hole in the bulk ADS space corresponds to a thermal state in the boundary CFT, where information is manifestly conserved. Although our universe is not an ADS space, the insights gleaned from this correspondence have sparked new avenues of research into how information might be preserved in more realistic settings. The idea of soft hair on black holes is another interesting thought. This idea says that black holes might have soft hair, which are small, low-energy quantum excitations on their event boundaries that could store knowledge about the matter they eat. These soft hair modes might be able to store information that is later released with Hawking radiation. This could be a way to solve the information problem without having to make big changes to quantum physics. Are Despite these advances, the black hole information paradox remains an open question, serving as a fertile ground for theoretical exploration. It challenges our understanding of space, time, and the very nature of reality, forcing us to confront the limits of our current physical theories. The resolution of the paradox may ultimately require a fully developed theory of quantum gravity, a framework that seamlessly unifies the principles of general relativity and quantum mechanics, and which could offer a definitive answer to how information is conserved in the most extreme environments. Relativistic jets and accretion disks. Black holes are very mysterious objects, but relativistic jets and accretion rings are two of the most interesting things that can be seen near them. They show us some of the most extreme physics that is going on. Matter that falls toward a black hole doesn't usually go straight in. Instead, it makes an accretion ring that swirls around the event horizon. This circle is made up of gas, dust, and other things. It slowly moves inwards because of gravity, while heating up at the same time because of friction and turbulent interactions. When the stuff inside the disk gets to millions of degrees, it gives off electromagnetic energy with a lot of different bands, from radio waves to X-rays. Astronomers can find black holes with the help of these signals, which also show how matter moves when it is subjected to very strong gravity forces. The process of accretion is a highly efficient means of converting gravitational energy into radiation. In many active galactic nuclei, AGN, the energy released by accretion can outshine the entire host galaxy. The luminosity of these systems is a direct indicator of the rate at which mass is falling into the black hole. Moreover, the structure of the accretion disk is often influenced by the spin of the black hole. A rapidly rotating black hole can drag the surrounding space-time along with it, a phenomenon known as frame dragging, which in turn affects the inner regions of the disk. This frame dragging effect can lead to the formation of a hot inner disk where the dynamics become even more complex and the radiation even more intense. In the process of accretion, relativistic jets are one of the most powerful effects. These jets are short blasts of charged matter that are thrown out from areas close to the black hole at speeds very close to light. More study needs to be done on the exact processes behind how jets form, but most scientists agree that a strong magnetic field and the black hole's rotation play a key role. Anchored magnetic field lines in the accretion disk twist and become very close together. This keeps some of the material going into the black hole away from its poles. This causes jets to form that can go for thousands of light years and take away not only mass, but also energy and rotational momentum. Observationally, these relativistic jets are among the most compelling evidence of black hole activity. Radio telescopes, in particular, have imaged spectacular jets emanating from the centers of galaxies, such as those seen in the radio galaxy M87. In some cases, the jets are so powerful that they influence the intergalactic medium, heating surrounding gas and regulating star formation in nearby regions. The jets also produce high-energy emissions detectable in X-rays and gamma rays, providing a multi-wavelength picture of these dynamic processes. Relativistic jets are not just visually striking, they are also key to understanding the feedback mechanisms that black holes exert on their host galaxies. As jets propagate through the interstellar medium, they can create shock waves that compress gas, potentially triggering new episodes of star formation. Conversely, they can also heat the gas to such high temperatures that it becomes resistant to gravitational collapse, thereby quenching star formation in some regions. This feedback is essential for explaining the observed correlations between black hole mass and galaxy properties, such as the M-sigma relation, and for understanding how galaxies evolve over cosmic time. The way that accretion disks and jets interact with each other also brings up interesting questions about how energy is changed in very harsh conditions. The speed with which accretion rings turn gravitational energy into radiation, and then use that energy to power jets makes it hard for us to fully understand how high-energy astronomical processes work. The motions inside these disks, caused by turbulence, magnetic reconnection, and viscous dissipation, are very complicated and are still a very active area of theoretical and computational study. Numerical models have gotten better at capturing these processes in great detail. They can now make predictions that are being tried against data from state-of-the-art instruments. Black hole spin, effects on spacetime and surrounding matter. The black hole's spin is an important feature that has a big effect on both the structure of spacetime close to the black hole and the motion of the matter around it. Schwarzschild black holes don't spin, but Kerr metric-described spinning black holes do. These spinning black holes have their own special effects that come from the way rotation and gravity interact. This rotation pulls the very fabric of spacetime along with it. This is called frame dragging, and it has huge effects on everything from how accretion rings are built to how powerful jets form. The spin of a black hole is quantified by a dimensionless parameter that ranges from 0, no spin, to 1, maximally spinning. As the spin increases, the black hole's event horizon shrinks, and the region outside it, known as the ergosphere, expands. Within the ergosphere, the dragging of spacetime is so extreme that no object can remain stationary relative to an observer at infinity. This region is of particular interest because it allows for the extraction of energy from the black hole, a phenomenon known as the Penrose process. In the Penrose process, particles entering the ergosphere can split, with one part falling into the black hole and the other escaping with more energy than the original particle possessed. This mechanism is one theoretical explanation for how relativistic jets, observed emanating from active galactic nuclei, might be powered. The impact of black holes' spin on the accretion disk is equally significant. In a spinning black hole, the inner edge of the accretion disk can extend closer to the event horizon compared to a non-rotating black hole. This proximity increases the efficiency of accretion, as gravitational potential energy is converted into radiation more effectively. The intense radiation, predominantly in the X-ray region, not only serves as an observational signature of the black hole's presence, but also affects the dynamics of the infalling matter, creating complex structures within the disk. Moreover, the twisted spacetime induced by spin can cause the disk to become warped or tilted, which in turn influences how material is channeled into jets. There are several places where observations show that black holes spin. Astronomers can study the reflection patterns in the accretion ring with X-ray spectroscopy, for example. Scientists can figure out the black hole's spin by looking at the iron K ± emission line and guessing the inner radius of the accretion disk. The disk is closer to the event horizon when the line is wider and more distorted, which suggests a faster spin rate. Finding gravitational waves from black holes merging also gives us separate information about spin, which helps us learn more about the rotational momentum of these space objects. The consequences of spin extend beyond individual black holes. On galactic scales, the collective effects of spinning supermassive black holes can influence the evolution of their host galaxies. The energy extracted via processes like the Penrose process can be channeled into relativistic jets, which, as we've seen, impact the interstellar medium by regulating star formation. These jets can heat the surrounding gas or even drive it out of the galaxy, thereby affecting the overall structure and evolution of the galaxy itself. Also, when spinning black holes interact with the dark matter ring around them, it can change the galaxy's gravitational potential, which could change how the stars circle and how the galaxy spins. So, the complexity that spin adds is very important in shaping not only the area around the black hole, but also the environment of the universe as a whole. Cosmic Censorship and the Nature of Singularities. Black hole physics' most fascinating problems center on the nature of singularities, points of infinite density where the known rules of physics fall apart, and the theory of cosmic censorship. Classical general relativity holds that a singularity results from stuff collapsing to a point producing infinite curvature of spacetime at the center of a black hole. But such infinities are usually seen as non-physical, implying that our present ideas could be lacking. Roger Penrose's cosmic censorship theory holds that these singularities are always concealed by an event horizon, therefore insulating the rest of the universe from the collapse of physical rules. Stated differently, nature censors the singularity, therefore preventing any observer from seeing its ultimate consequences. This conjecture is not a proven theorem, but rather a guiding principle that has shaped much of the research in gravitational physics. If true, cosmic censorship implies that all physically realistic black hole solutions are well behaved outside the event horizon, allowing for predictable evolution in the observable universe despite the unknown physics at the singularity. It also suggests that any breakdown in determinism is confined to regions that are causally disconnected from the rest of spacetime. Nonetheless, occasionally, numerical simulations and theoretical investigations expose situations contradicting the cosmic censorship theory. Under very particular and artificial circumstances, naked singularities, singularities not concealed by an event horizon, may occasionally develop. The prospect of such naked singularities begs serious issues concerning the ultimate consistency of general relativity and the predictability of physical laws. Though not yet seen, these situations inspire continuous investigation as physicists try to determine if cosmic censorship is a basic feature of nature or only a result of our present theoretical framework. The argument over cosmic censorship and the nature of singularities highlights a more basic difficulty in contemporary physics: the necessity of a unified theory able to effectively combine quantum mechanics with general relativity. Until such a theory is found, singularities will remain a mystery frontier, presenting both a problem and a possibility for new physics. Alternative theories of gravity in the context of black holes. Although Einstein's general relativity is still the pillar of our knowledge of gravity, other theories have developed that contradict and extend its predictions, particularly with regard to extreme phenomena like black holes. These ideas investigate changes to the basic equations of gravity, including impacts from quantum fields, additional dimensions, or new interactions that could become important in areas of strong gravitational curvature. FR gravity is one such method whereby the Einstein-Hilbert action is expanded by substituting a function fr for the Ricci scalar RRR. This change may provide various forecasts for the behavior of spacetime close to a black hole, hence perhaps smoothing out singularities or changing the development of event horizons. Another prominent idea is the framework of modified Newtonian dynamics, MOND, and its relativistic extensions, which attempt to explain galactic rotation curves without invoking dark matter. Although MOND primarily addresses galactic dynamics, its underlying concepts have spurred interest in alternative gravitational models that could have implications for black hole physics as well. For instance, these models might predict subtle differences in the gravitational potential around black holes, affecting the trajectories of nearby matter and the behavior of accretion disks. Extra-dimensional theories, such as those inspired by string theory or brane world scenarios, offer yet another perspective. In these frameworks, our familiar four-dimensional spacetime is embedded within a higher dimensional universe. The presence of additional dimensions can modify the gravitational force at small or very large scales, potentially altering the structure of black holes. For example, In some brane world models, black holes might lose mass into the extra dimensions or exhibit modified horizon geometries, leading to observable deviations from the predictions of general relativity. These alternative theories affect how we interpret observational data in real-world ways, making them more than simply mathematical oddities. The results are contrasted to the predictions of general relativity when astronomers use methods like gravitational lensing, X-ray spectroscopy, or even gravitational wave measurements to assess the characteristics of black holes. Any enduring differences might be a sign of novel physics, indicating that these other models describe gravity better under harsh circumstances. In this sense, alternative theories urge us to improve our comprehension of how gravity acts in the universe's most extreme conditions, both as a challenge and a supplement to Einstein's framework. These ideas may also help solve long-standing mysteries, like what singularities are and the black hole information paradox. Some changed versions of gravity models suggest ways to get rid of the troubling infinities at the center of a black hole. Instead of the singularity, they suggest changing it with an area of very high density that has a limit. These kinds of ideas not only help to clear up problems in theory, but they also make it possible to study quantum gravity in new ways. Impacts of black hole mergers, gravitational waves, and cosmic collisions. Some of the most exciting and dramatic things that can happen in the universe are black hole mergers. They are like cosmic labs where we can study the most extreme states of space-time. When two black holes spiral toward each other and finally join, they make a single, bigger black hole and send out huge amounts of energy in the form of gravitational waves. These changes in space-time, first predicted by Einstein's general theory of relativity and then seen by devices like LIGO and Virgo, have completely changed how we think about how heavy things interact with each other when they are under a lot of gravitational force. The process begins with two black holes orbiting each other in a decaying spiral due to the emission of gravitational waves. As they lose energy, the orbit shrinks and the black holes move ever closer, accelerating dramatically in the final moments before the merger. The collision itself is an incredibly violent event, generating a burst of gravitational radiation that carries away a significant fraction of the system's mass energy. This released energy is what allows us to hear the merging of black holes, even though no light is emitted during the event. Gravitational waves provide a unique observational window into these mergers. Unlike electromagnetic radiation, which can be absorbed or scattered by intervening matter, gravitational waves propagate almost unimpeded through space. Their detection has not only confirmed key aspects of general relativity, but has also opened up an entirely new field of astronomy. By analysing the waveform of these ripples, scientists can extract detailed information about the properties of the merging black holes, such as their masses, spins, and the distance to the event. These measurements are crucial for testing theoretical models of black hole growth and for understanding the population statistics of black holes across the universe. The effects of these huge crashes go beyond the basic physics of the merger and reach into the surrounding universe. When two black holes join, gravitational waves are created that can change the way matter moves around them. In crowded areas like the centers of galaxies, where black holes are common, these mergers may cause shocks in the medium between the stars. These kinds of shocks can squeeze gas clouds and maybe even start new star formation events, which would change how the home galaxy evolves. On the other hand, the energy released by the union can heat the gas around the star, which stops it from forming. This is called feedback. A key part of how galaxies change over time is the balance between sparking and stopping star formation. For black holes and galaxies to grow in a way that makes sense, the joining process is also very important. In the early universe, when galaxies were closer together, there were more mergers, which caused supermassive black holes to grow very quickly. Even though the rate of mergers has slowed down, black hole coalescence is still an important way for mass to build up in the centers of galaxies. So, studying these mergers tells us not only about the features of individual black holes, but also about how cosmic structures are made in general. Advanced numerical simulations have been indispensable in modeling black hole mergers. These simulations capture the complex, nonlinear dynamics of spacetime during the merger, providing predictions for the gravitational wave signals that are now routinely detected. By comparing simulation results with observational data, researchers refine their models and improve our understanding of how black holes interact and evolve. Furthermore, these simulations have shed light on the role of black hole spin and orbital dynamics in shaping the gravitational wave signal, offering insights into the angular momentum distribution of the colliding black holes. Time dilation near black holes and its implications. Gravitational time dilation is what happens when you are very close to a black hole and its strong gravitational field bends time itself. Einstein's theory of general relativity says that time moves more slowly for people who are in a stronger gravity field than for people who are in a weaker field. This impact is strongest near the event horizon of a black hole, where the gravitational pull is so strong that time can move at a crawl-like speed compared to how fast it moves farther away. Consider an astronaut travelling near to a black hole. As they approach the event horizon, their onboard clock will tick substantially slower than a clock located far away from the black hole's gravitational effect. For example, what appears to be only a few hours or days to the astronaut might take years or even decades for a safe spectator. This tremendous time dilation is more than a theoretical curiosity. It has been validated in a variety of experimental scenarios, albeit on much smaller scales, such as clocks in Earth's gravitational field. The mathematics underlying gravitational time dilation can be derived from the Schwarzschild metric. For a non-rotating black hole, the proper time tau experienced by an observer at a radial coordinate r is related to the coordinate time t by the equation. d tau equals the square root of 1 minus r sub s over r times dt, where RSRS is the Schwarzschild radius. As r approaches RSRSuris, the factor 1 minus rs over r. The square root of 1 minus rs over r, 1 minus rrs approaches 0, indicating that time nearly stops relative to an outside observer. This mathematical result encapsulates the idea that as one nears the event horizon, the effects of time dilation become extreme, effectively stretching the passage of time to infinity from the perspective of an external observer. Beyond the dramatic slowing of time, the implications of time dilation extend into the broader understanding of black hole interiors and the fate of objects falling into them. Once an object crosses the event horizon, all paths in spacetime lead inevitably to the singularity, a point where the curvature of spacetime becomes infinite, and our current understanding of physics breaks down. However, what happens to the flow of time inside the event horizon is still a matter of intense theoretical debate. Some models suggest that inside a black hole, the roles of time and space are interchanged. While an outside observer sees time as the dimension along which events evolve, an infalling observer might experience the radial direction, normally considered space, as a kind of inevitable time progression toward the singularity. This inversion of the traditional roles of space and time has far-reaching repercussions. If the singularity symbolizes more than simply a place, but an event in the future, the idea of an end for an item plunging into the black hole becomes unavoidable. According to this viewpoint, the singularity is more than just a place in space. It is also a moment in time when all matter is compacted into an impossibly dense state. This understanding challenges us to reconsider our assumptions about causality and the flow of time, especially when the gravitational field is so strong that traditional physics no longer applies. The significant temporal dilation seen near black holes poses fundamental problems regarding information transmission and preservation. If time practically stops at the event horizon, processes that occur there may appear frozen to an outside observer. This has important consequences for the black hole information dilemma, which asks whether information that goes into a black hole is lost forever. The way time is twisted in these extreme conditions may play an important role in how information is encoded on the event horizon and possibly liberated via Hawking radiation. Time dilation near black holes also has practical observational implications. For instance, if a star were to venture too close to a supermassive black hole, the time dilation effects could result in a prolonged and distorted light curve, as the star's emission is stretched over time. Such signatures can be used by astronomers to infer the presence of a black hole and to study the extreme physics in its vicinity. Inside a black hole, theoretical insights into its interior geometry. When an item passes through the event horizon of a black hole, our traditional concept of space and time begins to disintegrate. Inside this unknown zone, the fabric of space-time is warped beyond recognition, and the conventional principles of physics, as we know them, do not apply. Theoretical models predict that within the event horizon, the conventional roles of space and time may invert, implying that the radial direction, which normally represents distance, may instead become comparable to time. This significant change means that all routes within the black hole must eventually lead to the singularity, an endpoint where densities and curvatures become severe. Multiple theoretical theories have been suggested to try to figure out what might be inside, even though the inside can't be seen directly. One popular way is to use mathematical versions of the Schwarzschild and Kerr measures, which describe black holes that don't rotate and black holes that do rotate. These answers suggest that the inside of a black hole might be organized in strange ways, with paths or tunnels appearing from the chaotic area close to the singularity. Some theories even include the possibility that these tunnels could lead to other parts of spacetime, or even to completely different worlds. This thought fits with some multiverse theories. Quantum gravity is an interesting idea in another one. Many experts think that a theory of quantum gravity will be needed to fully understand what goes on inside black holes, because traditional general relativity doesn't work at singularities. It's possible that in this quantum world, the singularity is replaced by an area of finitely high density, where quantum effects smooth out the infinite curve that classical theories say would happen. In this case, information might be able to be kept safe, and the system's layout might be less harmful than was thought before. There are still a lot of unknowns about what goes on inside a black hole, but these theoretical ideas help us figure out what we know. A lot of people think that when you fall into a black hole, you might experience a huge change in the order of space-time, and time might stop existing in the way we know it. Singularities, the endpoint of collapse or a gateway to new realms. A singularity is the point where classical physics says the density and curve of space-time become endless. It is at the center of every black hole. However, singularities are not just places where everything ends. They are one of the most difficult problems in current physics. In classical general relativity, a singularity is thought to be what happens to matter when it collapses under the force of extreme gravity. It marks the point where our present models stop working. However, the idea of an infinite density is probably more of a sign that we don't fully understand gravity at the quantum level than a real thing. Many theoretical physicists now view singularities as potential gateways rather than mere endpoints. Quantum gravity, an as yet unresolved framework that seeks to merge general relativity with quantum mechanics, may offer alternative explanations. Some models suggest that instead of a point of infinite density, the singularity might be replaced by a region of extremely high but finite density, where quantum effects become dominant. In such scenarios, the classical singularity could be smoothed out, possibly giving rise to a new phase of space-time with different physical laws. This perspective opens up intriguing possibilities. For instance, if singularities are not the ultimate dead ends, but rather transitional states, they might serve as bridges or tunnels, connecting different regions of our universe, or even linking separate universes altogether. Such ideas are at the heart of speculative models, like the black hole cosmology, or the concept of a multiverse, where black holes might seed new, separate, expanding universes, a cosmic reproduction process sometimes referred to as cosmological natural selection. As far as observations go, we still don't know what singularities are made of because we can't directly look inside black holes. Still, progress in gravitational wave astronomy and high-energy astrophysics data give us secondary information that makes the traditional view less likely. For instance, measuring gravity wave signals from black hole mergers might show differences from what traditional general relativity says should happen, which could be a sign of the effects of a quantum-modified singularity. Cosmic cycles. Could black holes lead to a big crunch or big bounce? The idea of cosmic circles goes against the idea that the world has a single end that can't be changed. Instead, some ideas say that the universe might go through regular cycles of expanding and contracting, which is sometimes called a big crunch followed by a big bounce. In this light, black holes might not be the final resting places of matter. Instead, they might be very important in starting a new stage of cosmic growth. This concept revolves around the interaction between the general dynamics of the cosmos and gravitational collapse. Under the appropriate circumstances, it is possible that the expansion of a universe governed by gravity will finally slow, stop, and even reverse. The gravitational attraction may overcome the repulsive effects of dark energy if the density of matter exceeded a certain critical level, therefore causing the universe to collapse inward. Reflecting the circumstances at the moment of the Big Bang, this collapse, known as the Big Crunch, would compress all matter and energy into an extraordinarily hot and dense state. Black holes, with their tremendous gravitational influence, are natural laboratories for studying such collapse processes. When a black hole forms, it is essentially a region where matter has been compacted to a point where gravity dominates all other forces. As black holes merge and grow, they contribute to the overall gravitational pull in the universe. In some speculative models, these mergers and the continuous consumption of matter could set the stage for a cosmic rebound. Once the universe contracts to a sufficiently high density, quantum gravitational effects or pressure from fundamental fields might provide a counterforce to gravity, halting the collapse and triggering a rebound, a big bounce, where the universe begins to expand anew. This cyclic model of cosmic evolution offers an appealing resolution to some of the deep puzzles in cosmology. For one, it sidesteps the problem of an eternal heat death, where the universe gradually fades into a state of maximum entropy. Instead, each cycle resets the conditions of the cosmos, potentially diluting the accumulated entropy and allowing for the re-emergence of structure, energy gradients, and even the possibility of new forms of complexity. In this picture, the singularity at the end of a collapse is not a final state of nothingness, but rather a transitional phase, a gateway to a new beginning. The Big Bounce situation also gives us a way to think about how black holes might help the universe start over. Some ideas say that the huge amount of mass and energy that is concentrated in black holes might one day help create the right conditions for a new phase of growth. In these models, when a black hole collapses, it doesn't mean that matter ends. Instead, the very harsh conditions close to the singularity could cause a change in the quantum phase. This change could not only keep all the data from being lost, but it could also create a new world that is expanding and has its own physical rules. In a way, the things that happen inside black holes may be closely connected to the start of new cosmic cycles. This could be a case of cosmic natural selection, where worlds that make black holes well have a better chance of starting new ones. Although there is no hard data supporting the existence of a big crunch or big bounce, cyclic activity may be inferred from patterns in cosmic microwave background radiation and the universe's large-scale structure. In theory, next-generation observatories should be able to pick up on faint traces left by past cycles, illuminating the cyclical character of cosmic history. Black holes and multiverse theories. Infinite universes within black holes. The exciting expansion of cosmic cycle models suggests that black holes might be more than just the end of a world. They could be portals to new universes altogether, a thought that connects with theories of many universes. Within this hypothetical framework, it is possible for every black hole to contain its own universe, a newborn born from the gravitational collapse of matter. One alternative view is that black holes are cosmic seeds that, when combined with other forms of matter, create new areas of spacetime, each with its own unique set of physical characteristics. The idea is rooted in the peculiar nature of black hole interiors. As discussed earlier, within a black hole, the roles of space and time can be interchanged, suggesting that the singularity might not be a point of final destruction, but a transitional phase. Some theoretical models propose that quantum effects near the singularity could induce a bounce, leading to the formation of a new expanding region, a baby universe detached from our own. In this view, the parent black hole functions as a kind of cosmic incubator, where extreme conditions trigger the creation of new spacetime domains. This concept also provides an interesting perspective on the observed properties of our universe. For instance, if black holes spawn new universes, then our own universe might have emerged from such a process, with its physical constants and laws shaped by the conditions within its parent black hole. Moreover, the process of universe creation through black holes could be subject to a form of natural selection on cosmic scales. Universes that efficiently produce black holes may, in turn, generate more offspring, leading to a multiverse populated by an array of universes with varied properties. This idea is very speculative and can't be tested with the technology we have now, but it does open up exciting new study areas. As quantum gravity and observational cosmology continue to grow, they may provide indirect proof for this process. This could change how we think about black holes and the multiverse. Cosmological selection, survival of the fittest universes. The idea of cosmological selection is theoretical, but interesting. It takes the idea of natural selection and applies it to the worlds. The main idea is that if black holes can really create new universes, as multiverse theories say they can, then not all universes have the same chance to live or reproduce. Black holes would be more likely to form in worlds that have those characteristics. Over cosmic time, these universes would have more daughter universes. In this view, the physical factors and rules of our universe might not be random. Instead, they might be the result of a long process of cosmic reproduction, where only universes that are good at making black holes stay around and keep reproducing. The mechanism behind this idea draws parallels with biological evolution. Just as organisms with advantageous traits are more likely to survive and pass on their genes, universes that are optimized to produce black holes might generate more offspring in the form of new universes. These new universes could inherit similar physical laws and constants, though with slight variations, analogous to genetic mutations, which might in turn influence their ability to create black holes. Over countless cycles, a kind of cosmic natural selection could emerge, where the landscape of the multiverse becomes dominated by universes finely tuned for black hole production. If this process happens, it could have huge effects on our ability to comprehend why the physical constants we observe, have the values they do in our world. It makes me think that our universe might be one of many that are changing together, with its features being shaped by a process that supports conditions that are good for black holes to form. Even though this is just a theory at this point, it does offer an interesting way to connect how black holes change over time to how the universe as a whole has changed over time. There is a lot of room for thought here. We shouldn't just think about one universe. There could be a huge connected multiverse, and the fate of each universe depends on its ability to create new cosmic areas. Implications for the nature of space, time, and reality. Not only do black holes make us question what we think we know about matter and gravity, but they also make us question what space and time are made of. Einstein's general theory of relativity gives us a traditional view of how space and time are connected. It says that space and time make a dynamic continuum that bends when mass and energy are present. With their very strong gravity fields, black holes make a powerful example of how these two forces interact. Space-time is twisted so much near a black hole that the normal rules we take for granted don't work anymore. Time slows down, and the lines between the past, present, and future become less clear. Time dilation gets stronger as you get closer to a black hole, according to both observations and theories. People who are close to the event horizon feel time moving much more slowly than people who are far away. This event not only shows how time can change when gravity forces are strong, but it also brings up important questions about what time order is. When it comes to black holes, the line between space and time starts to blur. For example, inside the event horizon, many models say that the radial direction, which is usually thought of as spatial, actually acts like time, pulling everything toward the singularity. This switching or mixing of layers goes against what we normally think and makes us think about time as something that can change, not something that stays the same. The behavior of space and time near black holes offers clues to the potential unification of quantum mechanics and general relativity. The extreme conditions near a black hole's event horizon are a natural laboratory for testing new theories of quantum gravity, where the smooth fabric of space-time predicted by relativity might be replaced by a more granular quantum structure. In this regime, space and time might be composed of discrete units, or quanta, that could provide a deeper explanation for phenomena like Hawking radiation and the information paradox. These insights suggest that our classical concepts of space and time are emergent properties that arise from a more fundamental quantum reality. The effects go beyond the field of theoretical physics. How we describe the world and guess what will happen to it in the end depends on how well we understand space and time. To give you an example, if quantum effects near black holes change the structure of space-time, then the history of the universe may be much less static and more dynamic than was once thought. We have to rethink long-held beliefs about causality and the arrow of time, because it's possible for time to stop or act in a way that isn't linear in extreme situations. Philosophical implications, black holes, reality, and our place in the cosmos. People have been interested in black holes for a long time, both for their strange physical features and for the deep psychological questions they raise about what reality is and where we fit in the universe. The fact that they exist questions the way we usually think about time, place, and cause and effect. We have to question the basic nature of time development when we think about how black holes can bend space-time so much that time itself slows down and, in some readings, may even turn around. Are the known flows of past, present, and future real, or are they properties that appear out of a deeper, more complicated reality that is controlled by gravity and quantum effects? This uncertainty invites us to reflect on the nature of existence. If black holes can obscure, scramble, or even potentially preserve information in ways that defy classical logic, then the notion of an end, whether it is the end of a star, a galaxy, or even the universe itself, takes on a more nuanced meaning. The idea that the universe might ultimately be a product of cyclic processes, with black holes playing a pivotal role in cosmic rebirth, challenges the linear narrative of creation and destruction that has long dominated both science and philosophy. In this view, endings are not final. They are merely transitions to new states of being, echoing the ancient philosophical notion of eternal recurrence. Study of black holes compels us to reconsider our place in the universe. The realization that such colossal and mysterious entities exist, and that their behavior might underpin the evolution of the cosmos, can instill a sense of both humility and wonder. It suggests that our understanding of reality is still in its infancy, and that there may be layers of truth yet to be discovered, layers that could redefine our comprehension of life, consciousness, and the interconnectedness of all matter. Astrophysical limits. What stops black holes from swallowing everything? Despite their formidable gravitational pull, black holes are subject to fundamental astrophysical limits that prevent them from devouring the entire universe. First, a black hole's influence is localized. Its gravity only dominates within its event horizon, while the vast expanses between galaxies are governed by the overall dynamics of cosmic expansion. Even the most massive black holes cannot affect matter that is not sufficiently close. Moreover, as black holes grow, their average density decreases, reducing the intensity of their gravitational pull per unit volume. This counterintuitive property, where increased mass leads to a larger but less dense black hole, ensures that the gravitational capture of distant matter is limited. In addition, the accelerating expansion of the universe, driven by dark energy, further isolates black holes from the surrounding cosmos, preventing them from merging uncontrollably into a universal absorber. Cosmic expansion's role in preventing universe-swallowing black holes. While black holes exert immense gravitational pull locally, the universe's accelerating expansion plays a crucial role in preventing them from engulfing everything. Dark energy drives this expansion, causing galaxies and other structures to recede from one another at an ever-increasing rate. As a result, even if a black hole were to grow by accreting nearby matter or merging with other black holes, its influence remains confined to a limited region of space. The expansion effectively dilutes the density of matter in the universe, ensuring that the mass is too spread out for any one black hole to capture it all. This cosmic stretching acts as a counterbalance to gravitational attraction on large scales, isolating black holes within their host galaxies and clusters, and thereby safeguarding the overall structure of the cosmos. Technological advances in black hole research. The technology and observing methods used to study black holes have changed a lot in the last few decades. What used to be a field of theory is now full of real-world data. New camera designs, gravitational wave monitors, and computer models have given scientists tools they've never had before to study these mysterious objects. One of the most important steps forward has been the creation of high-resolution cameras that can take pictures of the areas around giant black holes. For example, the Event Horizon Telescope, EHT, was able to take the first picture of a black hole's shadow in the galaxy M87. This worldwide system of radio telescopes forms a dish about the size of Earth, which lets scientists see the bent spacetime near the event horizon in great detail. This kind of direct image not only backs up what general relativity says, but it also shows how matter behaves in very strong gravity fields. In parallel, advancements in X-ray and gamma-ray astronomy have opened up additional windows into black hole activity. Satellites like the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope monitor the high-energy emissions from the accretion disks surrounding black holes. As matter spirals inwards, it heats up and emits radiation across the electromagnetic spectrum. Detailed spectral analyses of this radiation allow scientists to infer the properties of the black hole, such as its spin and the structure of its accretion disk. These high-energy observations have proven essential for understanding how black holes interact with their host galaxies and for tracking the energetic outbursts associated with black hole mergers. Another major leap in black hole research comes from the field of gravitational wave astronomy. The groundbreaking detections by the Laser Interferometer, Gravitational Wave Observatory, LIGO, and Virgo have confirmed that black hole mergers produce ripples in spacetime, gravitational waves, that can be measured on Earth. These observatories use laser interferometry to detect minute changes in distance caused by passing gravitational waves, offering a new means of listening to the cosmos. The data from these detections not only provide independent measurements of black hole masses and spins, but also test the very foundations of general relativity under extreme conditions. Gravitational wave astronomy has rapidly evolved into a powerful complement to traditional electromagnetic observations, enabling a multi-messenger approach that enhances our overall understanding of black hole physics. Along with big steps forward in observation, big steps forward in computing have made it much easier to predict how black holes move. Numerical models that are up to date now let scientists look at complicated processes like accretion, jet formation, and black hole merging in 3 dimensions. By combining the ideas of general relativity with fluid dynamics and magnetohydrodynamics, these models give us a moving picture of how matter acts near a black hole. They make it possible to try and improve theory models in a virtual lab. As computers get faster and better, thanks to progress in high-performance computing and even quantum computing, these models should become more accurate. This will help us learn even more about how matter and energy behave in very strong gravity fields. Additionally, better detection sensitivity and data processing have made it possible to study weak signs that were previously hidden by noise. More and more, machine learning methods are being used on very large datasets that come from sensors on Earth and in space. These techniques can sort through huge amounts of data to find trends and outliers that could point to new or strange behavior in black hole systems. Using both AI and standard data analysis together is speeding up findings and improving our models of how black holes work. In essence, the technological advances in black hole research have transformed our capacity to observe, model, and understand these complex objects. From the first images of a black hole's shadow to the detection of gravitational waves from cataclysmic mergers, each new innovation builds on our understanding of extreme gravity and the evolution of cosmic structures. These breakthroughs not only confirm long-standing theories, but also challenge us to refine our models of the universe. As technology continues to advance, the future of black hole research promises to unveil even more profound insights into the nature of space-time, matter, and the fundamental laws governing the cosmos. Future prospects. What new observations could reveal about black holes? Future black hole research looks to be as groundbreaking as it has been in the last several decades. Future observing facilities and technical developments are expected to offer even better knowledge of these mysterious phenomena and the extreme physics controlling them. With ideas for improved gravitational wave observatories and next-generation telescopes, researchers are ready to explore black hole surroundings with hitherto unheard-of accuracy. Making tools that are more sensitive and have better resolution is one of the most exciting things that could happen. For example, the next wave of very long baseline interferometry, VLBI, networks will build on what the Event Horizon Telescope did well by taking more detailed pictures of black hole shadows and how their accretion rings move. It is believed that these new arrays will be able to resolve smaller structures closer to the event horizon. This will help us understand how magnetic fields, relativistic jets, and the spinning matter that feeds these cosmic giants interact with each other in complex ways. In parallel, advancements in gravitational wave detectors are on the horizon. Planned projects like the Laser Interferometer Space Antenna LISA, and the Einstein telescope will expand our observational window into gravitational waves, covering frequency ranges that ground-based detectors like LIGO and Virgo cannot access. These space-based observatories will be particularly adept at capturing the gravitational waves emitted by supermassive black hole mergers and other slow, subtle cosmic events. Such observations will not only provide more precise measurements of black hole masses and spins, but may also uncover entirely new classes of gravitational wave sources, offering fresh insights into the life cycle of black holes and the evolution of galaxies. Multi-messenger astronomy will continue to grow in importance. By combining electromagnetic, gravitational wave, and neutrino observations, researchers can cross-verify findings and build a more comprehensive picture of black hole environments. For example, simultaneous observations of a black hole merger in both gravitational waves and X-rays could reveal details about the dynamics of the surrounding accretion disk and the role of magnetic fields during the merger process. Improvements in computer power and methods for analyzing data will make these monitoring attempts even better. Better numerical models and machine learning techniques will help sort through very large data sets, finding small patterns and outliers that might point to new physical phenomena. With these tools, researchers will be able to test theory models more accurately and might find evidence that questions what we think we know about black holes right now. Black holes and the evolution of life. Black holes are usually thought of as damaging cosmic engines, but they may have also helped make the universe a better place for life in a way we didn't expect. At first glance, black holes' strong gravitational pull and violent processes make them look like they wouldn't be good places to live. However, black holes have effects that go far beyond their immediate surroundings. Galaxies can change over time through their formation, growth, and energy feedback loops. These loops can help create the complex environment needed for life to start. We will talk about how black holes may have shaped the beginnings of life by controlling star formation in the centers of galaxies and adding chemicals to the space between stars. We will also talk about how studying these processes is giving us new ideas about our place in the universe. Black hole influence on life largely results from their role in galactic development. At the nuclei of most large galaxies, supermassive black holes regulate the dynamics of the surrounding gas and stars. Often seen as high-energy radiation and powerful jets, the next energy output from a black hole actively accretes stuff may heat and disperse gas inside the galaxy. Most critically, this process regulates star formation is active galactic nucleus, AGN. One side of things, the strong outflows can compress nearby gas clouds and trigger starbursts. On the other hand, these same outflows might warm the interstellar medium to temperatures that prevent the gas from cooling and condensing into new stars. This delicate equilibrium ensures that galaxies remain stable by guaranteeing either too few or too many stars do not evolve. Black holes are sort of cosmic thermostats that regulate the conditions under which planets, and perhaps life, can develop. The chemical enrichment of galaxies is another avenue through which black holes indirectly foster life. The massive stars that eventually collapse to form black holes also produce heavy elements through nuclear fusion. When these stars explode as supernovae, they eject enriched material into space. This process, combined with the recycling of gas through AGN feedback, spreads elements like carbon, nitrogen, oxygen, and iron throughout the galaxy. These elements are essential for the formation of rocky planets and the complex chemistry required for life. Without the cycle of stellar evolution and the subsequent role of black holes in regulating galactic environments, the building blocks of life might be far scarcer. Furthermore, black holes could affect galaxy design in such ways as support for long-term planetary stability. Black holes in galactic centers' gravitational interactions serve to define star orbits and can cause orderly galaxy structures to develop. A well-ordered galactic environment raises the possibility that planetary systems will remain stable across billions of years, therefore offering the consistent circumstances required for life to evolve. On the other hand, chaotic or too active areas can upset planetary orbits, creating unfavorable conditions less fit for life. Beyond these galactic-scale processes, the study of black holes is also inspiring new ideas about life's potential in extreme environments. Researchers are investigating whether life could emerge in the unique settings near black holes. Although the immediate vicinity of a black hole is extraordinarily hostile due to intense radiation and gravitational forces, the regions just outside the event horizon, where matter is heated and expelled, may create pockets of energy that drive unusual chemical reactions. Some theorists have even speculated that, under the right circumstances, extreme environments influenced by black hole activity could foster prebiotic chemistry or even support exotic forms of life that are adapted to high-energy conditions. While this remains highly speculative, it opens up new lines of inquiry regarding the diversity of life in the universe. The dynamic interplay between black holes and the cosmic web of galaxies may have implications for the broader evolution of the universe. The cumulative effect of AGN feedback across billions of galaxies could influence the large-scale distribution of matter and energy, ultimately affecting the overall rate of cosmic expansion and the thermal history of the universe. This grand-scale influence may determine how long the universe remains hospitable for life, and whether cycles of cosmic rebirth, such as those proposed in some cyclic models, might reset the conditions for life to emerge anew. Investigating black holes and how they affect galaxy development also motivates multidisciplinary inquiry, combining astrophysics, planetary science, chemistry, and even biology. Analyzing the extreme surroundings of black holes helps scientists not only with the physics of these unusual phenomena, but also with the basic mechanisms behind the development of complexity in the cosmos. By means of telescopes capable of peering far into galaxy centers and gravitational wave detectors capturing the echoes of black hole mergers, we may create a more complete picture of how the cosmic environment is formed throughout time as we improve our observational methods. Black hole research and technological innovation. In the search to learn more about black holes, some of the most amazing technical advances have been made. Black hole research used to be mostly theoretical, but in the last few decades, big steps forward in observational tools, data processing, and computer models have turned it into a lively, multi-messenger field that is always pushing the limits of technology. This part talks about how progress in studying black holes has led to new ideas in many different types of technology, ranging from high-resolution imaging systems to advanced gravitational wave monitors and cutting-edge modeling methods. The direct image of a black hole's shadow is one of the most important steps forward in the study of black holes. The first picture of the supermassive black hole in galaxy M87 was taken by the Event Horizon Telescope, EHT, which is a global network of radio stations working together through very long baseline interferometry, VLBI. By combining data from telescopes around the world, this amazing feat was made possible. This created a virtual telescope the size of Earth. The EHT project's success not only proved important general relativity forecasts, but it also raised the bar for how accurately astronomy images can be made. Ultra-high frequency transmitters, atomic clocks for time synchronization, and advanced data correlation systems are some of the technologies that make up the EHT. They are used for more than just studying black holes. They are also affecting progress in geodesy, telecommunications, and remote sensing. At the same time, progress in high-energy astronomy has made it much easier to study black holes indirectly. Space telescopes, like the Fermi Gamma Ray Space Telescope and the Chandra X-ray Observatory, keep an eye on the strong X-ray and gamma-ray signals coming from accretion rings around black holes. These telescopes use high-tech detectors that are very sensitive to high-energy photons and can pick them up and study them. The technology made for these devices has led to new ideas in materials science for radiation-hard detectors, high-speed data processing, and cold cooling systems. These improvements not only let us see into the very dark places near black holes, but they can also be used in medical imaging, security scans, and particle physics studies. In the field of gravitational wave science, there has been another huge step forward: the Laser Interferometer. Gravitational Wave Observatory, LIGO, and its European equivalent Virgo have changed the way we think about black hole mergers by finding the tiny changes they make in space-time. There are very small changes in distance, about 1/100th of the diameter of a proton, that happen when gravity waves pass through Earth. These devices use laser interferometry to measure these changes. Building these devices was hard from an engineering point of view, but it led to progress in areas like laser stability, vibration isolation, and precision metrology. As a result, technologies have been used in areas as different as tracking earthquakes, making precise tools, and quantum optics. The complexity of simulating black hole dynamics requires solving the equations of general relativity coupled with fluid dynamics and magnetohydrodynamics. High-performance computing clusters and sophisticated numerical algorithms now allow researchers to create detailed three-dimensional simulations of accretion flows, jet formation, and black hole mergers. These simulations not only help interpret observational data, but also guide the design of new experiments by predicting what we should see under various scenarios. The development of such simulation software has fostered innovations in numerical methods, parallel computing, and even machine learning, which is now increasingly used to analyze vast datasets from telescopes and gravitational wave detectors. Machine learning itself has emerged as a powerful tool in black hole research. Advanced algorithms can sift through enormous volumes of observational data, ranging from high-resolution images to gravitational wave signals, to identify patterns and anomalies that might otherwise be overlooked. These techniques enable real-time data processing and adaptive feedback, improving the sensitivity of detection instruments and allowing for more precise characterization of black hole properties. The synergy between machine learning and traditional astrophysical methods is accelerating discovery, optimizing observation schedules, and even helping to refine theoretical models. Because black hole study involves a lot of different fields, it has led to partnerships that go beyond normal boundaries. Engineers, computer scientists, and physicists now work together to make systems that mix tools for observations, data processing, and theoretical modeling. This setting of working together has led to new ideas that aren't just related to astronomy. For instance, methods created for analyzing gravitational wave data are being used to check on the health of structures in civil engineering. Similarly, image technologies created for the EHT are having an impact on progress in medical diagnosis. If we look to the future, studying black holes will likely lead to even more technology advances. Next-generation telescopes, like the expected improvements to the EHT and the future gravitational wave observatories in space, like LISA, will need even more powerful tools and ways to look at the data they collect. Not only will these advances help us learn more about black holes, they will probably also lead to the creation of new tools that could be used in many areas of science and business. The role of black holes in space exploration and colonization. Recently, they have come up in theoretical talks as a possible way to start exploring space and even settling there. The harsh conditions close to these objects make them look like the final resting place for stars and planets. However, Recent progress in both theory and technology suggests that the unique qualities of black holes could be used to help space travel and getting resources. The thought of using black holes as natural energy sources is one of the most unlikely but interesting ones. When matter falls into a black hole, it gives off a huge amount of energy, mostly in the form of high-energy radiation and strong relativistic jets. Black holes could be a key part of modern power systems if we can figure out how to safely get their energy and use it. Using the energy from accretion disks or the rotating energy of spinning black holes through processes like the Penrose process could theoretically make it possible for spaceships to move faster than chemical or even nuclear rockets. This method might make it possible to move at speeds close to light, which would make the huge distances between stars more doable. The science of wormholes is another interesting area that could be used for space travel. Many scientists and engineers are interested in the idea that wormholes, which are imagined paths through space-time, could form naturally or even be made artificially near black holes. This idea is still very much in the realm of theoretical physics speculation. In theory, if exotic matter could be used to secure a wormhole that could be travelled through, it might be possible to move instantly between faraway parts of space. This would change the way we explore space by making it possible to travel quickly across the galaxy or even between galaxies, without having to worry about the speed of light. Even though it won't be used in real life for a long time, studying the quantum features of black holes and how they might be able to make structures that look like wormholes is pushing the limits of what we know and what technology can do. Black holes may serve as gateways to harnessing unique gravitational effects that could assist in space navigation. The intense curvature of space-time near a black hole offers a natural laboratory for studying gravitational assists, a technique already used in planetary flybys to boost spacecraft speeds. In the distant future, advanced spacecraft might use controlled approaches to the gravitational fields of black holes to perform extreme slingshot maneuvers, gaining significant velocity without expending large amounts of fuel. Such methods would require precise navigation and control systems, but the potential for dramatic speed increases could open new horizons for deep space missions. In addition to being useful for guidance and movement, black holes may also be able to be used to use resources that are already there. For instance, the accretion ring around a black hole is full of heavy elements that were made by stars that lived a long time ago. If we can find ways to get these elements out of the ground safely in the future, they could be used to build spaceships, shelters, or even fuel for fusion reactors. At the moment, it is not possible to directly extract resources from black holes because the conditions are too dangerous. However, as autonomous robotic systems and advanced materials continue to develop, it may become possible to tap into these cosmic reservoirs. This would turn black holes from destructive forces into sources of energy and matter. Apart from pragmatic uses, black hole research is already guiding the construction of next space missions. Inspired by the Event Horizon Telescope, instruments able to image the shadow of a black hole are now being developed for additional high-resolution astronomical investigations. These technical developments are opening the path for next-generation observatories fit for the long-term missions needed for deep space exploration, platforms either in orbit or on the Moon. Moreover, in astronomy, a multi-messenger approach is resulting from the cooperative efforts of gravitational wave detectors, X-ray observatories, and radio telescopes. This synergy not only clarifies black hole dynamics, but also helps us to identify and track other severe cosmic events that can influence colonization and space travel. Using black hole physics for space exploration has ramifications for strategic planning of human migration throughout the universe. The capacity to travel great distances fast, use enormous energy resources, or even inhabit other worlds becomes even more crucial as humans consider the long-term survival of our species. Although the idea of using black holes for these uses is yet hypothetical, It forces us to rethink on cosmic levels, propulsion, energy generation, and resource extraction. Ideas traditionally limited to science fiction, such as wormhole bypasses or black hole-powered spacecraft, are progressively becoming seen as valid scientific endeavours. The theoretical frameworks developed to understand black holes are already influencing how we conceive future space habitats and energy infrastructures. Research into quantum gravity and the nature of spacetime might one day yield practical methods for manipulating gravitational fields or controlling the extreme energies near black holes. Such breakthroughs could revolutionize not only space travel, but also terrestrial applications, leading to more efficient energy systems and advanced materials capable of withstanding extreme conditions. Philosophical, cultural, and ethical implications of black hole science. The conflict between classical determinism and quantum uncertainty drives all of these questions. Black holes seem to challenge the prevailing notion based on quantum physics that all knowledge about a physical system is retained across time. This conflict, best represented by the black hole information paradox, has generated fierce philosophical discussion about whether some features of reality are intrinsically unexpected, or if the cosmos is essentially changeable. Some intellectuals contend that the seeming loss of knowledge in black holes pushes us to rethink the notion of causation generally. From this perspective, the irreversible collapse of matter and the possible scrambling of information question our ingrained belief in a linear, unidirectional passage of time, and imply instead that time might be more flexible and linked than first thought. The cultural impact of black hole research is equally profound. Throughout history, humanity has looked to the stars for inspiration, and black holes have emerged as powerful symbols in literature, art, and film. They represent both ultimate destruction and the possibility of rebirth, a cosmic cycle where endings might be the precursors to new beginnings. This duality has resonated deeply with existential and metaphysical ideas in many cultures, reinforcing themes of impermanence and transformation. In science fiction, for example, black holes often serve as portals to alternate dimensions or as mechanisms for time travel, reflecting our collective fascination with the unknown and our yearning to transcend the limits imposed by nature. These narratives not only entertain, but also influence public understanding of complex scientific ideas, making the abstract concepts of astrophysics accessible and emotionally resonant. Ethical considerations also emerge as black hole science advances. The pursuit of knowledge in this domain is intertwined with technological innovation, which in turn raises questions about how such technology should be applied. As we develop instruments capable of imaging black holes, detecting gravitational waves, and even simulating extreme conditions through quantum computing, we must ask ourselves, how will these technologies impact society? Could advancements driven by black hole research lead to unforeseen applications, both beneficial and potentially hazardous? For instance, the same high-precision measurement techniques and computational methods used to study black holes might eventually be adapted for surveillance, defense, or even altering gravitational fields on Earth. Such possibilities call for a careful ethical review and the establishment of guidelines to ensure that scientific progress benefits humanity without compromising safety or privacy. The possibility of using energy from very strong gravitational conditions offers both benefit and risk. Though these are intriguing, ideas like harvesting energy from black hole accretion disks or harnessing gravitational slingshots for space travel also challenge us to address cosmic resource distribution and environmental responsibility. Should humankind ever be successful in using such enormous energy sources, it will have to address problems of fair access, sustainability, and possible ecological disturbance, not only on Earth, but also perhaps on other celestial worlds. Black hole science makes us think about our place in the universe in a more philosophical way. The idea that our universe could be a part of a bigger, more related cosmos, or that black holes could create new universes, makes us question what our existence means. This way of thinking sees human life not as a single event, but as a part of an endless circle of making things and changing them. This point of view can make us feel both humble and hopeful by telling us that our search for knowledge is part of a bigger story in the universe that goes far beyond our world. Thank you for joining us on this mind-bending exploration of black holes and their potential to engulf the cosmos. If you found this dive into the mysteries of the universe as fascinating as we did, make sure to subscribe, like, and share this video to spread the wonder. We'd love to hear your thoughts. What do you think about the idea of a universe swallowed by a black hole? Leave a comment below and stay tuned for more cosmic adventures as we continue to push the boundaries of science and explore the unknown.